The work I will present you today is titled Careful with That, Observation of Human Movements to Estimate Object Properties. Humans manage to easily manipulate objects they have never used before. They start by inferring their properties, such as the weight, the stiffness, or the fragility, observing the objects and other people manipulating them. Then they use tactile and force feedback to improve the estimation. In human-human interaction, this ability to infer the object properties from others' manipulation is linked to motor resonance. The same set of neurons are activated both during the execution and during the observation of an action, and this provides a common description of our and others' behaviors. Since we perfectly know the consequences of our own actions, when we observe others, we can immediately recognize and understand what they're doing. For instance, observing another person lifting an object allows us to correct eventual misconception we may have about its weight, given by misleading external features such as the shape or the dimension. To promote a natural and efficient interaction, robotic platforms that support humans in daily activities should have similar abilities. If we consider a scenario where the robot acts as a helper in an unconstrained environment, estimating the characteristics of the objects handled by the human acquires a great importance. As a consequence, the robot can plan a safe and efficient motion action, perhaps being cautious if the object is fragile or slippery. The scientific question we address in this study is, can the features of an object be inferred just by looking at the human transporting it? In particular, we focused on two features that influence how we manipulate an object. The first one, the weight, is familiar for everyone, and for example, it influences the velocity we adopt to lift an object. Differently from the weight, the concept of carefulness is not trivial. Previous studies have dealt with delicate objects, but they focus more on robotic manipulation, where the difficulty was given by the item's stiffness or deformability. In our study, we consider the carefulness necessary to move an item from a wider perspective. Indeed, not only the object's stiffness, but also the content about to be spilled, the risk for the object to fall, or its fragility, may lead a person to perform a particularly careful manipulation. We hypothesize that, by knowing kinematic feature descriptive of the transport movement, it is possible to infer the carefulness required in the manipulation of the object, and also to discriminate if the object is heavy or light. To start the study, we acquired the data of 15 participants. They seated at a table and had to perform a series of reaching, lifting, and transportation movements of the objects. Every time they pressed a key on the keyboard, the volunteer was instructed by a synthetic voice indicating the position on the shelf of the object to be transported. The volunteer performed a reaching action toward the specified position, grasped the object, moved it from the shelf to a scale on the table, and then released the object and returned to the resting pose. The same procedure was followed to move the object from the table towards one of the shelves. The objects we used for glasses were characterized by the two features we introduced before, the weight and the carefulness required in their handling. What we may call fragility was not given by the glass material, that was plastic, but by the presence of water inside two of the glasses that were full till the brim. The fact that in front of the table there was a robot with all the electronics made the transport of these glasses particularly risky. The two levels of weight, that differed for 500 grams, were obtained instead with coins and screws, balancing the eventual presence of water inside a glass. The objects were identical in shape and appearance, and their transparency was chosen so that participants could clearly see the content of the glass and appropriately plan their movements. The data used in this study was collected using two different sensors, which were synchronized through the middleware YARP. The first sensor was a motion capture system, and it was used as a ground truth. The kinematic of the human motion was recorded through active infrared markers placed on the right hand. The other source of information was the ICAB left camera. The humanoid robot was placed opposite to the table and was simply a passive observer. No collaboration with the participants took place. As motion descriptor from the saved raw images, we choose to compute the optical flow, following an approach already tested for the detection of biological motion in the scene. In this method, the optical flow is computed for every time instant, estimating the apparent motion vector for each pixel of the image. Since we wanted to distinguish the features of the object during the transportation, it was necessary to isolate this phase in every trial. To do so, we took advantage of the experiment design. Indeed, each trial presented three clearly identifiable phases: a reaching action, from the resting pose to the position occupied by the glass, either on the shelf or on the table, the transportation movements, and finally the departing back to the resting position. The segmentation was then performed by placing a threshold of the 5% on the second peak of the norm of the velocity. The same set of motion representation was then extracted from both the motion capture data and the optical flow. The features we extracted were the velocity, the angular velocity, the curvature, and the radius of curvature. These features can be easily estimated at every time instant, and these ideally allow to classify the object before the end of the observed action, allowing the robot to prepare for the possible handover. Here you can see some examples of transport movements with the four glasses. In the first row, we have the light glasses with the two different levels of carefulness required. While in the second row, there are the heavy glasses, and again, it can be appreciated how the presence of water influences the transport movement. For us, it's easy to distinguish at least between the careful and uncareful movements, but to obtain an answer in an automated way revealed to be challenging. So, after isolating the transportation phase and extracting the same set of features from both the sources of data, we adopted a deep learning approach. The goal of the classification is to discriminate between the two possible features of the transported classes, the carefulness level associated with the object and its weight. Therefore, we decided to approach the problem using two binary classifiers, one for each feature. Previous studies suggested that the use of neural networks, such as convolutional or long-term memory, is a good solution for classifying time-dependent data. Due to the characteristics of the glasses, the duration of the transport movement varied consistently among the trials. To obtain sequences with the same number of samples for each trial, they were resampled and those data were used to train the first model. However, the resampling can be performed only knowing the start and the end of the transportation phase. Since in an online scenario this information may be not available, a further attempt was performed using layers able to handle temporal sequences of different lengths. In this case, a common zero padding and masking technique was adopted. The shorter temporal sequences were completed with zero values, and those values were then ignored during the training. This way, the length of the longest transport movements was preserved. Such data were used to train the second model. The dataset consisted of 14 participants. Indeed, one was excluded as outlier, since revealed to be particularly careful, even with the glasses without water inside. A leave-one-out approach was adopted, repeating the training of the models with 13 participants and testing the performances with the 14th. An ADAM optimization algorithm was chosen, and for the early stopping, it was used a categorical cross-entropy as loss function. Here are the results for the classification of the carefulness in the movements. You can see the accuracies for both the models, using the features extracted from the motion capture data in shades of blue, and from the optical flow in shades of green. The performances with both the sources of data are really good, and the fact that the optical flow gives an accuracy above 85–90% is promising for implementing such classification ability directly on the robot. The classification of the weight was more difficult, and the results are not good. With this approach, we obtained an accuracy around 60% for the first model trained with the motion capture data, while around 55 in the other cases. This result may be due to different concurrent factors. The presence of water in some of the glasses may have led the subjects to focus mainly on the carefulness feature, unconsciously overlooking the weight difference between the glasses. Moreover, previous studies have showed how the vertical component of the velocity in a movement is informative about the weight transported. In this dataset, there was a great variability in such sense, since the movements were going from the table to the shelves, from top to bottom, and vice versa. The first classifier was tested against these two hypotheses, but no significant improvements in the accuracy have been achieved. A possibility for future works is to focus on the vertical component of the velocity and explore this additional hypothesis on reasonably extended datasets to obtain more reliable results. The fact that, despite the variability in the data, the carefulness classification works so well is an encouraging step into pursuing this approach online with the robot. For future works, as I already mentioned, it is necessary to improve the classification of the weight, exploring other motion features, and reducing the variability in the dataset. It should be also noted that the movements were acquired in a non-social context. The participants were simply asked to move the glasses from one position to another, but no communicative intention was required, since no collaborative task was going on. It is possible, as the signaling theory suggests, that in a collaborative context their gesture would become more communicative of the object features, to facilitate the partner, going beyond the kinematics adjustments adopted to optimize the movements. This study supports the research in human-robot interaction in the direction of addressing complex situations in realistic settings. In this context, the robot could rely on implicit signals to facilitate the cooperation with a human partner. Even objects that are not intrinsically fragile, but that have an effective value for us, could be handled with carefulness by the robot, as long as the delicacy in our gestures is detectable. The classification approach we proposed relies exclusively on the body kinematics. It overlooks all the external appearance of the object, and this grants the ability of generalizing over previously unseen items. Thank you so much for your attention.